Hey everyone. Today, we're diving deeper into the world of electric motors, building on what we discussed in the last video. If you haven't had a chance to check it out yet, I highly recommend you do so. It'll give you a solid foundation for what we're covering today. Of course, if you're already familiar with the basics of electric motors, feel free to jump right in. In this video, we'll be unraveling the fundamental principles behind AC induction motors, how they operate, and how they consume electrical power. Understanding these concepts is crucial for anyone wanting to be qualified and certified energy manager or expert. Let's get started. Let's start with perhaps the most common rating you see on a motor, horsepower, or HP. This isn't a measure of electrical input. It's the principle of motor output power. The HP rating specifies the maximum mechanical output power the motor is designed to deliver at its rated voltage, frequency, and full load. However, a motor doesn't always run at full HP. It will deliver only the power required by the equipment it's driving. This brings us to the concept of operating load, which is simply the actual mechanical power the motor is producing, expressed as a percentage of its rated HP. Now, a motor isn't a perfect machine. It loses some energy as heat and other factors. This brings us to the principle of motor efficiency, represented by the Greek letter eta. Efficiency is the ratio of the useful mechanical power the motor outputs to the total electrical power it consumes from the source. Think of it as output divided by input. Rearranging that, the electrical input power, or the power the motor actually draws, is equal to the mechanical output power divided by the efficiency. This input power, which does the work and covers losses, is what we call real power, P, measured in watts or kilowatts. Most industrial motors are three-phase. For a three-phase system, there's a specific relationship between the apparent power, S, the line voltage, VL, between any two phases, and the line current, IL, flowing in each wire. This is the principle of the three-phase power formula. Apparent power, S, equals the square root of 3, multiplied by the line voltage, multiplied by the line current. As you can see on the slide, S equals square root 3 multiplied by V, multiplied by I. We use this formula constantly to calculate current when we know the apparent power and voltage. Now, here's a critical principle that sometimes causes confusion: the principle of load-dependent performance. The efficiency and power factor values for a motor are not constant. They change depending on how much load the motor is pulling. While a motor nameplate gives values, these are typically the full load efficiency and power factor. If a motor is running at partial load, its actual efficiency and power factor will likely be different. This is why, in accurate analysis, you need the efficiency and power factor at the specific operating load you're interested in. Let's shift gears slightly and talk about motor speed. A key concept is synchronous speed, S. This is the theoretical speed at which the magnetic field inside the motor is rotating. It's determined by the design of the motor's windings, specifically the number of motor poles. The stator winding creates magnetic pole pairs. The total number of poles, always an even number, 2, 4, 6, 8, etc., is a fundamental factor in determining speed. More poles mean a slower rotating field for a given frequency. This leads us to the principle of operating frequency impact. Running a motor at a frequency different from its design frequency will fundamentally change its speed. But it's not just speed. Altering the frequency, especially if voltage isn't adjusted proportionally, impacts the motor's torque capability, its maximum power output, how it draws current due to changing impedance, and even how effectively its cooling fan works. Motors are optimized for a specific frequency range, and operating outside that range requires careful consideration or specialized control, like a variable frequency drive, VFD. Now, let us discuss some problems related to electric motors and the principles that we discussed earlier. A 100 HP motor is running at 75% loading on 480-volt three-phase electric power and 90% efficiency. Power factor is 85%. What amperage is it consuming? We want to determine the amperage drawn by this 100 HP motor operating under specific conditions. First, let's list what we're given. We have a motor rated at 100 horsepower. It's running at 75% of its full load. The power supply is 480 volts, and it's a three-phase system. At this operating point, the efficiency is 90%, and the power factor is 85%. Our goal is to find the input current, or amperage, that the motor is consuming. We always start with what the motor is doing mechanically. The HP rating is the motor's maximum capability. Our motor is running at 75% of its 100 HP rating. So, the actual mechanical output power is 100 HP times 0.75, which equals 75 HP. Now, we need this in watts for our electrical calculations. Remember our conversion. 1 HP equals 746 watts. So, 75 HP multiplied by 746 watts per HP gives us 55,950 watts. This 55,950 watts is the real mechanical power output of the motor at this load. Next, we use efficiency to figure out the electrical power going into the motor. Efficiency is output over input. We know the output power, 55,950 W, and the efficiency, 90%, or 0.9. We can rearrange the efficiency formula to find the input power. Input power equals output power divided by efficiency. Let's calculate the real input power. 55,950 watts divided by 0.90. That comes out to approximately 62,166. 67 watts. This 62,167 watts is the real electrical power the motor is drawing from the source to produce 55,950 watts of mechanical output, accounting for the internal losses. Now we bring in the power factor. Power factor relates the real power we just calculated to the apparent power that the source must supply. Apparent power is real power divided by the power factor. The power factor is given as 85%, or 0.85. Let's calculate the apparent input power, 62,166. 67 watts divided by 0.85. This gives us approximately 73,137. 25 volt amperes VA. This is the total apparent power being pulled from the 480 volt, three-phase lines. This value directly relates to the current. Finally, we use the three-phase power formula to find the line current. Remember, apparent power, S, in a three-phase system is the square root of 3 times the line voltage, VL, times the line current, IL. We want to find IL, so we rearrange the formula. IL equals the apparent power, S, divided by the product of the square root of 3 and the line voltage, VL. We have our values. S is 73,137, 25 VA, and VL is 480 volts. The square root of 3 is approximately 732. Plugging in the numbers. IL equals 73,137, 25 VA divided by 732 multiplied by 480 V. Let us do the math. IL equals approximately 97 amps, or 88 amps. So, the calculated amperage the motor is consuming under these conditions is about 88 amps. By following these steps, starting from the actual mechanical output, accounting for efficiency to find real electrical input, using power factor to find apparent power, and finally using the three-phase formula, we can determine the current draw of the motor. Now, second problem, let's look at another practical example, this time focusing on the impact of efficiency on energy consumption. We have a scenario where an old 100 HP motor is being considered for replacement with a new, more energy-efficient 100 HP motor. Both motors are doing the same job, running at 80% load. The old motor has 85% efficiency at this load, and the new one has 90% efficiency at the same load. Our goal is to calculate how much electrical input power is saved by switching to the new motor. The key here is that both motors are performing the exact same mechanical work, driving the same load at the same speed, assuming negligible slip difference. This means their mechanical output power is the same. The difference in their efficiency directly translates to a difference in the electrical input power they require to produce that same output. A higher efficiency means less input power needed for the same output. First, let's determine the actual mechanical power output. Both are 100 HP motors running at 80% load. Actual output power equals 100 HP multiplied by 0.80 is equal to 80 HP. Now, convert this to watts, as this is the power unit we'll use with efficiency. Remember 1 HP is 746 watts. Actual output power in watts equals 80 HP multiplied by 746 W per HP equals 59,680 watts. This 59,680 watts is the mechanical power output for both the old and the new motor at 80% load. Now, let's use the efficiency of each motor to find their respective electrical input powers. Remember, input power equals output power divided by efficiency. For the old motor with 85% efficiency, or 0.85, input power old equals 59,680 watts divided by 0.85. Calculating that, the old motor draws approximately 70,211 watts. For the new motor with 90% efficiency, or 0.90, input power new equals 59,680 watts divided by 0.90. Calculating this, the new motor draws approximately 66,311 watts. Notice the new motor draws less power because it's more efficient, even though it's doing the exact same work. The energy savings is simply the difference between the power the old motor uses and the power the new motor uses. Savings equals input power old minus input power new savings equals 70,211 watts minus 66,311 watts. The difference is approximately 3,900 watts or 3.90,065 kilowatts. This is the power saved. So, by replacing the old 85% efficient motor with the new 90% efficient motor when running at 80% load, we save about 3.9 kilowatts of electrical power. This example clearly shows the direct impact of even a seemingly small increase in efficiency on the actual power consumption and potential energy savings, especially for motors that run for many hours. Let's move on to another fundamental concept for AC motors, synchronous speed. As we discussed earlier, this is the speed at which the magnetic field inside the motor's stator rotates. It is a critical speed because the motor's rotor tries to follow this rotating field. For an AC induction motor with 3 pole pairs, 6 poles, the actual supplied frequency is 40 Hz, cycles per second. What is the synchronous speed of the motor at 40 Hz? Here is the problem we will solve. We have a motor with 3 pole pairs, which means it has a total of 6 poles. It is connected to a power supply with a frequency of 40 Hz. We need to find its synchronous speed in revolutions per minute, or RPM. The synchronous speed is determined by the frequency of the power supply and the total number of poles in the motor. The formula is straightforward. Synchronous speed equals 120 times the frequency in Hertz, divided by the total number of poles. Let's apply the information from our problem to the formula. The frequency, F, is given as 40 Hz. The motor has 3 pole pairs. Since each pair has 2 poles, the total number of poles, P, is 3 multiplied by 2, which equals 6 poles. Now we plug these values into our formula. Synchronous speed equals 120 multiplied by 40 Hz, divided by 6 poles. 120 times 40 is 4,800. So, synchronous speed equals 4,800 divided by 6. Performing that division, we get 800 RPM. This calculation is fundamental to understanding motor speed. The actual speed of an induction motor will always be slightly less than this synchronous speed when it's under load, due to slip, but the synchronous speed sets the upper limit determined by the power supply and the motor's design. In this video, we delved into the core principles of electric motors and explored their practical applications in addressing real-world business and energy challenges. Don't miss out on our other videos for more insights into the exciting fields of energy and sustainability. Subscribe to our channel to stay updated.